Welcome to the deep dive.
Great to be here.
Today, we're really getting into the weeds of distributed consensus. We've lined up 10 key questions from our source material to sort of guide us.
Yeah, it's our roadmap, you could say. The goal is understanding what this thing is and, maybe more importantly, why it's so fundamental.
Absolutely. It sounds like the kind of invisible plumbing that makes so much of the digital world actually work.
That's a good way to put it. It's like the hidden agreement keeping these huge networks of computers, well, on the same page.
Okay, let's jump right in. Question one, what is distributed consensus, really? And why should you care?
Simply put, it's the challenge of getting a bunch of separate computers, like servers in a data center, to all agree on a single decision or value.
Agree on something specific.
Exactly. And why care? Well, think about things you relied on: online banking, cloud storage, booking systems. Without consensus, you could have chaos.
Chaos-like.
Like your bank balance showing two different amounts depending on which server you hit, or maybe a database update getting lost. Consensus is basically the bedrock for making these distributed systems reliable and consistent.
Okay, so it's stopping digital anarchy.
Yeah.
Got it. Now, our sources mention Paxos and Raft. Where do they fit in?
Paxos and Raft. They're probably the most famous algorithms for achieving this consensus. They're like detailed instruction manuals.
Instructions for agreement.
Pretty much. They specify exactly how computers should talk to each other, propose values, and ultimately decide on one, even if some messages get lost or some computers crash.
Right, because things do go wrong. That was another point, the challenge of doing this over unreliable networks.
Exactly. Real-world networks are messy. Packets drop, they get delayed, sometimes even arrive out of order. Plus, individual machines can just, fail.
So the algorithms have to expect that.
Robust ones do, absolutely. They're designed from the ground up to tolerate a certain amount of failure and network weirdness and still guarantee agreement.
Okay, so if machines can fail, how do they coordinate? That leads to this idea of leader election, doesn't it?
It often does, yes. Many popular algorithms, and Raft is a really clear example here, elect one machine to be the leader.
And the leader calls the shots.
Sort of. It coordinates the decision-making process. It simplifies things quite a bit because the other machines, the followers, mostly just respond to the leader.
But what if the leader fails?
Good point. The algorithm must have a mechanism to detect that failure and elect a new leader.
Yeah.
That's critical.
So the leader is key to keeping things safe. And what was the other term? Liveness.
Correct. Safety and liveness, they're crucial properties. Safety basically means the system never makes a wrong decision.
Wrong meaning inconsistent.
Yeah, like different parts of the system agreeing on different things. Safety guarantees that if a decision is reached, it's the same decision everywhere it matters.
Okay. And liveness.
Liveness means the system eventually does make a decision. It won't just get stuck forever, I'm able to agree, assuming, enough of the system is actually working.
That's reassuring. Now, one question really hit on why it's apparently so hard to get consistency, availability, and partition tolerance all at the same time. Sounds like a fundamental conflict.
You've definitely hit on a core challenge there. It's often framed by the CAP theorem, though the sources didn't explicitly name it. Think about a network split part of your system can't talk to the other part.
Okay, like a network partition.
Right. Now, do you prioritize consistency, meaning both sides must have the absolute latest identical data? If so, the side that can't confirm with the other might have to become unavailable until the network heals.
I know.
Or you prioritize availability, meaning both sides keep working. But then they might make independent decisions, leading to inconsistencies when the network reconnects. You often have to choose which property to compromise on during a partition.
Makes sense. A tough balancing act. So going back to failures, how exactly do algorithms like Raft handle individual computers just dying?
Well, good consensus algorithms are designed to be fault-tolerant, usually up to a certain number of failures. If a follower fails, the leader just stops talking to it. If the leader fails.
Oh, a new election happens. We covered that.
Exactly, and this often works hand in hand with replication.
Replication. Like making copies of data.
Precisely. You store the same data on multiple machines. If one machine holding the data fails, the data isn't lost. But then you absolutely need consensus.
To make sure all the copies stay consistent when something changes.
Got it. Consensus ensures that updates are applied to all replicas in the same order, keeping them synchronized. Think database clusters, distributed file systems, even cryptocurrency ledgers. They all rely heavily on this interplay between replication and consensus.
Okay, so let's try a quick wrap. Distributed consensus. It's about getting scattered computers to agree. Super important for reliability. Algorithms like Paxos and Raft provide the how-to. They have to deal with messy networks and failing machines, often using a leader.
And wrestling with that fundamental trade-off between consistency and availability during network problems.
Right. And it's deeply linked to keeping replicated data,
Yeah.
backup copies, in sync.
Couldn't have said it better.
Yeah. So here's a final thought to leave you with. As our systems get ever more complex, more distributed, more interconnected, what new possibilities open up because we can achieve this reliable agreement? And conversely, what new, maybe unforeseen challenges are lurking in this ongoing quest for perfect distributed consensus? Something to ponder. Thanks for joining us for this deep dive.